Hello and welcome to the MOOC on Antennas course. My name is Fernando. I am professor at the University of Oviedo, and I'm going to talk in this part about the geometry and field at the aperture of a kind of reflector, the most known, which is the parabolic reflector. Why a paraboloid has a reflector antenna? So this is because of its geometry. The paraboloid geometry allows to obtain a uniform aperture field in phase, resulting in a high directivity antenna. So once we place a radiating source in the focus of a paraboloid geometry, what we obtain finally at the aperture is a field that is going to be constant along the aperture in phase. Not in amplitude, but it is going to be constant in phase. So this makes that the final radiation pattern of the whole antenna is going to have a high directivity, which is one of the main purposes of this kind of antennas. So the basis of reflector antenna analysis, we are going to consider a ray tracing theory, geometry optics, because typically the antennas are electrically large, several wavelengths. So this is a high frequency approximation that can be considered when in Maxwell equations we turn the wavelength to 0. In the reflector analysis, the medium will be supposed to be homogeneous, rays rectilinear, and the fields behave locally as plane waves. When the ray is incident to the reflector surface, this surface will be supposed to be a perfect electric conductor, and both the Snell law and the boundary condition about the total tangential electric field equals 0 must be satisfied. So in this figure you can observe the reflecting of an incident plane wave over a perfect electric conductor with an incident direction and the reflected one, and also the incident and reflected fields which have been decomposed into a vertical and horizontal component. So according to the Snell law for reflection, both angles of incident and reflection with respect to the normal direction have to be the same, and from that we obtain the reflected direction in this way. And considering also the boundary condition, that means that the sum of the incident and reflected vectors of the electric field must be 0 in its tangential component. Finally, we arrive to that both incident and reflected fields in amplitude are the same, and we can obtain also the polarization of the reflected fields in such a way that the vertical components of the electric fields, incident and reflected, are the same, and the horizontal components are opposite in direction. So according to the Snell law and boundary condition of the electric field, we go further and establish the geometrical equation that defines the paraboloid, both in Cartesian components or in polar components. This is a two-dimensional representation. And according to ray tracing, from the focal point, any ray, reflected ray, turns into an horizontal ray that goes towards an aperture which we will consider that is normal to the axis of this parabolic reflector, that will be the zeta axis. So according to this ray tracing at the reflected rays, we can see that all reflected rays are horizontal, parallel, and becomes like a plane wave towards the aperture. So we can say that this geometry transforms a spherical wave radiated from its focus into a plane wave. And the most significant characteristics is that the optical path from the focal point towards the reflector surface and then to a given point of the aperture is the same for any other ray traced from the focal to the aperture and then to the reflector surface and then to the aperture. That comes directly from the equation of the parabolic reflector antenna. So this optical path is going to be constant for any reflecting point. And we can say that the fields are on phase at the aperture if the feed phase center is at the focus and of the parabolic reflector. This is the really most important characteristic of the parabolic reflector. Typically, the geometrical parameters that define the parabolic reflector are the d, diameter, and focal length f. That is the distance from the focal point to the reflector at this axis direction. But there are other alternatives to define, and one of them is the so-called half angle theta sub O. And from the equations of the parabolic reflector, it turns out very fast that there is a relation between this half angle theta sub O and the ratio f over d, which is the well-known focal length over distance, which defines typically a reflector antenna when we have to select it from a given feed antenna, or if we have defined the f over d parameter, then we have to design the appropriate feed antenna. So in the next slide, we are going to try to define what is the model of the field at the aperture in the case of a parabolic geometry. First, we will consider that in the focus we have a feed antenna, typically a horn antenna of input power P, gain G, and polarization is Y unit vector. So considering far field conditions, spherical wave, we can relate the gain to the power density flux, which depends on the incident field. So from these equations we have the amplitude of the incident field, and we will consider that it propagates from the focus to the reflector surface as a spherical wave, and this is the reason of this exponential phase term. After reflecting, and due to the Snell law and tangential field conditions at the reflected field in amplitude will be the same as the incident field. So finally, propagating this reflected field to the aperture, we will consider that it propagates as a plane wave, and that's the reason of this exponential propagation factor, phase propagation. So finally, what we obtain at the aperture is an equation in which we have polarization E sub r, and depends of the root square of the input power gain. We have the term of the distance from the focus to the reflector, and an exponential term, which is the phase, and that we see that is a constant phase. This is the important consequence of the parabolic geometry. Also, we have the polarization defined according to the Snell law. So finally, if the feed typically illuminates the reflector with some symmetry of revolution and linear polarization, the field at the aperture can be simplified in this way. One important parameter is that we call the edge illumination. That means how the reflector antenna is illuminated at the edge of the reflector compared with the illumination at the center of the reflector. So basically it is a ratio between the incident field at the reflector in this theta sub O angle with respect to the center of the paraboloid. And the expression in logarithmic form depends on the ratio of the gain of the feed antenna, typically the horn antenna, at the edges of the reflector and in the direction of the axis of the paraboloid, and another term which depends on the difference of distance between the distance focus to the edge of the reflector and the distance from the focus to the center of the reflector. We will use this parameter in order to perform an optimum parabolic reflector antenna. Just talking a little about polarization, we have calculated it in the model of the aperture with ideal fit. That means, for example, cos-q pattern. There is no cross-polar radiation on the aperture. If the fit is linearly y-polarized, there is no x-field components of the aperture. And if the fit has some cross-polar radiation, the radiated fields also have cross-polar components in this far-field radiation. In fact, with the real fit, for example, polarized along y-axis and symmetric pattern, the cross-polar at the aperture has the same values, but in opposite directions, in adjacent quadrants. So finally, the radiated cross-polar component is 0 on the main planes and is maximum in the bisecting planes, typically at phi equal 45 degrees. This is in this image at the bottom right place. You can observe the typical behavior in a 45 degrees plane with the main lobe and the maximum of the cross-polar. So with this, we conclude this part of reflector antenna course regarding to geometry and field at the aperture. Thank you very much.